In the vastness of our solar system, Jupiter stands out as a colossal enigma, captivating scientists and astronomers for centuries. Just when we think we understand this gas giant, it defies our assumptions. With its unpredictable behavior and fascinating storms, with winds reaching speeds of 640 kilometers per hour, and the mysteries of the metallic oceans hidden in its core, Jupiter continues to baffle scientists. Join us on an extraordinary journey as we explore the depths of this enigmatic world and uncover its secrets. Logo. Decades of meticulous studies have revealed the impressive complexity of Jupiter. Recently, an additional 12 moons orbiting the gas giant were discovered, bringing the total number of satellites around Jupiter to 92, more than any other planet in the solar system. These new moons range in size from 1 to 3.2 kilometers, and most of them have extensive orbits. 9 out of the 12 moons take more than 550 days to complete one orbit around the planet. Scientists believe that due to the movement of these distant moons in the opposite direction of Jupiter's rotation, they may be captured asteroids. For a long time, Jupiter was believed to act as a protective shield, safeguarding our planet against threats from outer space. Astronomers even suggested that this was one of the reasons life had a chance to evolve on Earth. However, recent discoveries cast doubts on Jupiter's role as a celestial guardian of Earth. Long-period comets, originating from the distant regions of the solar system and taking millennia to orbit the Sun, often approach our neighborhood. However, thanks to Jupiter's gravitational influence, most of these fast-moving icy comets are flung out of the solar system before they come close to Earth. Therefore, the chances of long-period comet collisions with our planet are extremely rare, occurring over millions or even tens of millions of years, and Jupiter's presence plays a crucial role in protecting Earth from these potential impacts. However, the gravitational forces of the gas giant have both positive and negative effects on life on Earth. On one hand, its immense gravity prevents nearby space rocks from accumulating and forming a planet, resulting in the asteroid belt, a collection of scattered fragments between Mars and Jupiter. However, Jupiter's gravitational attraction continues to influence the asteroids, causing some to deviate toward the Sun. This change in their trajectories increases the chances of collisions with Earth, as we have witnessed in the past. In 1770, Comet Lexell passed by at an extraordinarily close distance of 1 million miles from our planet in astronomical terms. It is believed that this comet originally came from the outer regions of the solar system and experienced a close encounter with Jupiter that redirected it toward Earth. After completing 2 orbits around the Sun, the comet returned close to Jupiter 9 years later, and it was then ejected from the solar system. The Jupiter shield theory, supported by previous computer simulations, suggested that the gas giant expelled many long-period comets from the solar system, and this theory correctly predicted the impact of comet Shoemaker-Levy 9 on Jupiter in 1994. However, the computational resources available at the time were not as advanced as today's, and scientists had to perform extensive calculations. Now, we have data that includes a larger number of short-period comets and near-Earth asteroids compared to long-period comets. New simulations show a different perspective. Jupiter's gravitational influence interacts with the asteroid belt, causing gravitational resonances that eliminate solitary asteroids and redirect them into the inner solar system. Collisions between asteroids can also contribute to this process, dispersing rocky fragments into resonance zones. The inner edge of the asteroid belt is particularly affected by a phenomenon called secular resonance, which directs material into the inner solar system. Jupiter's current mass allows it to redirect both comets toward Earth, as was the case of Comet Lexell, as they effectively remove them from the solar system. If Jupiter had only 1/5 of its current mass, it would still destabilize comets but would not be able to remove many of them, resulting in a higher rate of impacts on Earth. The frequency of impacts plays a crucial role in the long-term evolution of life on a planet. The geological record of Earth indicates that a rate of one major collision every 100 million years provides enough time for the biosphere to recover and thrive. However, a higher rate of impacts occurring every few million years could devastate the planet and hinder the development of a new biosphere. Some scientists believe that collisions with Earth also contributed to the arrival of water here. But what about water on Jupiter? For the first time in 1995, the presence of water vapor on Jupiter was detected. The Galileo spacecraft was responsible for this discovery, conducting extensive observations and measurements of the planet and its moons. Instruments on board Galileo, especially the near-infrared mapping spectrometer, identified water vapor in Jupiter's atmosphere during a close flyby. Recent data reveals that water represents about 0.25% of Jupiter's atmosphere above the equator, which, despite seeming small, is an immense amount of water. Jupiter, likely the first planet to form in our solar system, contains a significant amount of gas and dust that did not become part of the Sun. Knowing the amount of water present on Jupiter is crucial for scientists studying the formation of the solar system. In recent years, a team of researchers used telescope data to discover a substantial amount of water within Jupiter's famous Great Red Spot. Launched by NASA in 2012, the Juno spacecraft is currently orbiting the gas giant, capturing close-up images of its clouds. Equipped with advanced instruments, Juno has revealed even more evidence of water on Jupiter. Due to its mass, which is more than twice the sum of all the other planets in our solar system, even small fractions of water on such a massive planet represent a significant amount, much larger than the amount of water found on Earth. The presence of water in the atmosphere of the gas giant is also responsible for the mesmerizing displays of lightning on Jupiter, which are 100 times brighter than Earth's lightning, along with the peculiar hailstones. Lightning has been detected in Jupiter's water clouds, where water droplets collide with electrically charged ice crystals. However, the Juno spacecraft has also observed faint lightning at higher altitudes in the atmosphere, where temperatures drop to approximately -87 degrees Celsius -125 degrees Fahrenheit, too cold for water to exist in a liquid state. So how do lightning occur in these conditions? The answer to this mystery lies in ammonia, notable component in Jupiter's atmosphere that acts as a natural antifreeze. In the upper atmosphere, water ice crystals combine with ammonia vapors and melt. These water-ammonia droplets then collide with additional ice crystals coming from below, creating an electric charge that generates lightning. Below the ammonia ice clouds, the water-ammonia droplets continue to grow until they become so heavy that they can no longer stay suspended in the air, resembling large hailstones like those we have on Earth. Scientists believe that these hailstone-like objects descend deeper into Jupiter's atmosphere. However, now let's delve even deeper into Jupiter's inner layers. Previously, it was believed that the gas giants in our solar system had a rocky core, a theory that was widely accepted for a long time. However, scientists have recently started to question this theory. Utilizing data from Juno's orbit, scientists are investigating how matter is distributed within Jupiter, and recent findings have revealed an unexpected mystery hidden in the core of this gas giant. Jupiter's core is subject to extremely high pressures, much greater than those found on Earth, and temperatures that can reach up to 20,000 degrees Celsius (36,000 degrees Fahrenheit). To understand these conditions, scientists use powerful lasers to compress samples and simulate the planet's pressures in the laboratory. The Center for Matter at Atomic Pressures, CMAP, at the University of Rochester is leading this research. The composition and physical properties determine the density of materials in Jupiter's core. Recently, scientists have discovered that the core is not as compact as previously imagined. Only 18% of the material in its deepest regions is rocky. Jupiter is mainly composed of hydrogen, accounting for about 90% of its composition, along with approximately 10% helium and small amounts of other elements. In the outer layers of this gas giant, hydrogen exists as a colorless and transparent gas, just like here on Earth. As you go deeper into Jupiter, the increasing atmospheric pressure transforms hydrogen into a dense and peculiar fluid that conducts electricity like a metal. So, what is this substance? About 10% of the way toward Jupiter's core along its radius, the immense volume of hydrogen gas that forms the atmosphere compresses into a singular form called metallic hydrogen liquid. This liquid metallic hydrogen exhibits properties similar to water, with low viscosity, excellent electrical conductivity, and efficient thermal conduction. Inside Jupiter, this abundant substance turns the planet into an immense source of energy. On Earth, elements can exist as solids, liquids, or gases depending on temperature and pressure. While hydrogen is typically a gas on our planet, it can be artificially compressed and cooled to become a liquid or solid. However, even in those phases, hydrogen maintains its non-metallic nature, exhibiting low heat and electrical conductivity. In contrast, metals are excellent conductors of heat and electricity due to their atomic structure. In the interiors of the gas giants in our solar system, hydrogen is subjected to extreme temperatures and pressures, allowing for peculiar states, including liquid metallic hydrogen. Under these conditions, hydrogen atoms lose their electrons, resulting in a mixture of free hydrogen nuclei and electrons. This electron mobility is similar to the behavior of a metal. One theory suggests that Jupiter may harbor vast oceans of liquid metallic hydrogen in its core, which could be 12 to 45 times more massive than Earth. This layer of liquid metallic hydrogen, with a depth of about 40,000 kilometers, combined with Jupiter's rapid rotation, generates a colossal magnetic field that extends over an impressive distance of 725 million kilometers, making it the largest in our solar system. This magnetic field has its own mysteries. By exploring the depths of Jupiter's atmosphere, scientists have discovered a new area called the Great Blue Spot, distinct from the storm known as Jupiter's Great Red Spot. The Jovian magnetic field, which is 20,000 times stronger than Earth's, originates from a wide area in the northern hemisphere and returns near the southern pole, and researchers have identified a concentrated region near the equator, the Great Blue Spot. This area exhibits fluctuations in the intensity of magnetic fields of up to 1% per year, strengthening and weakening in different regions. The extended mission of the Juno probe until 2025 will provide additional evidence to evaluate hypotheses about Jupiter. As we continue our journey of discovery, the mysterious depths of Jupiter hold even more surprises to be unveiled. Stay tuned to be the first to witness new cosmic wonders, and thank you for joining us on this journey. Subscribe and see you next time. Subscribe to the Nebula Mind channel to not miss the upcoming videos.